It is my absolute privilege to welcome you to this special edition of our Talkshow series, our International Women's Day special. A happy Women's Day to you all. Before we begin, let me take just a moment to tell you about who we are. Because the Geoscience Society itself is a story worth telling. We are a student initiative, a few of us, passionate about the earth beneath our feet, the minerals in its crust, the forces that shape our planet, came together with one simple but ambitious idea. What if all geoscience students had one common platform? One umbrella under which we could all learn together, grow together, and be inspired together. No boundaries of college or university, just a shared love for geosciences. That's what the Geoscience Society is, born from a conversation among students, built by students, and dedicated to every student who has ever looked at a rock and wondered about how the story it holds. Our talk show series is one of our flagship efforts, bringing accomplished professionals directly to our community so that the gap between the classroom and the field just becomes a little smaller. And today, on International Women's Day, we couldn't have chosen a more fitting occasion or a more inspiring guest. The theme of today's talk is Finding Art's Resources for Shaping Up a Better Tomorrow, an insight on exploring critical and
অর্কদা মিউট হয়ে গেছে। অর্কদা বলছি মিউট হয়ে গেছে।
I'm sorry, I'm sorry. Uh, the theme of today's talk is Finding Art's Resources for Shaping Up a Better Tomorrow, an insight on exploring critical and precious minerals. At a time when the world is racing toward clean energy and sustainable development, the minerals beneath the Earth's surface have never mattered more. And the scientists who find and study them are among the most important of our generation. Our speaker today is one such scientist, a geologist, a gazetted officer, and a remarkable inspiration. Our host will tell you much more about her incredible journey in just a moment. Please join me in giving a very warm welcome to Miss Namrota Saha. With that, I'd like to hand over to our host for the evening, Koena De, who will formally welcome all of you and take us through the program from here. Over to you, Koena. Thank you.
Good afternoon, everyone. Thank you, Arkupratim, for the introduction. Once again, in behalf of the Geoscience Society, I warmly welcome all of you to today's session of our talk show. I am Koena De from Jadavpur University, and currently I am the co-lead of the social media team. And today I'll be your host for today's program. Before we begin, I would like to thank all of you for the amazing response to our previous talk show. Your enthusiasm and participation truly made it a memorable and successful event. Today, we are pleased to have with us Ms. Namrota Saha, who completed her graduation in geology from the Ashutosh College and post-graduation from the IIT ISM Dhanbad. She is currently working as geologist, Group A gazetted officer at GSI Western Region, Jaipur. In today's session, she will be sharing her knowledge and insights on exploring Earth's resources, along with her journey in the field of geoscience. You all are welcome to share your thoughts and questions in the chat box during the session itself, and we'll try to take them up along the way as the discussion progresses. Now, without further delay, let us warmly welcome Ms. Namrata Saha and begin today's talk. Over to you, ma'am.
Hello, everyone. Am I audible and can I be seen?
Yes, ma'am.
Yes.
In both the links? Okay.
Yes.
Okay. Hello, everyone. I'm Namrata Saha. Currently, I'm working in Rajasthan under Geological Survey of India. I'm a geologist here, and mainly for the past 4 years, I'm doing exploration. So, kind of, we can say it's an exploration geologist point of view that you're going to get. I'm not a very high professional, but I am a basic person who is still learning, and I'm just sharing how much learnings I have gone so far with. And of course, you guys are all invited in to suggest, to help me learn too. Maybe you will have a very different point of view to what I am going to show today, and it will be very beneficial. This discussion is going to be very fruitful for all of us. So, shall we start?
Yes, ma'am.
Is the slide visible and is it changing?
Yes, ma'am.
Oh, okay. Okay. So, hello everyone. I'm going to present on finding of Earth's resources for shaping up a better tomorrow and insight on exploring critical and precious minerals. Okay. First of all, let's discuss what is exploration geology. Exploration geology is a subject that may not be introduced in bachelor's, because in bachelor's what we get to see is a basic geoscience data generation, like how to study lithology, how to do structures, and how to do geomorphology, and how to read a map, and how to locate yourself, how to what to do when we go to the field. And we are showed in a very random process, like we are locating ourselves, we are seeing a lithology, we are structuring and everything, and the rest of us, we will have to correlate all these together, and then we form a map, we become a geologist, basically understanding each of these topics and then correlating them in one line makes us a geologist, a proper field geologist. Next comes is exploration geologist. Once you have already done with the lithology, once you have already understood the structures, you know petrography, you know the basics, like there are lab studies, various kinds of like SEM, IPMA, and a lot of lab studies for a deeper knowledge of the rocks that you are seeing raw in a hard specimen. So basically, after you are done with all the basics, next is how can we use our knowledge next to do something better for our country, do something better for our society. What is our contribution in helping upholding India's pride? Okay, so that is when we come to exploration geology. So exploration geology is basically we are identifying, we are locating, and we are evaluating the grades and the quantity of the resource that we are having in a particular area. Okay, so that is exploration geology. Next comes is when we talk about exploration, next comes is what are we exploring. So what are we exploring has two parts. One is in which areas we are exploring. Next is which time this particular resource has been made by Mother Earth, that we have come across it and now we are trying to find it. So when we talk about the time and when you talk about the space, it's completely two different terms that comes into our mind. One is metallogenic epoch, which relates to the time, and one is metallogenic province, which relates to the this space. So time and space together sounds as metallogenic epoch and metallogenic events. Metallogenic province. So when we talk about metallogenic epochs, what are we talking about? We are exactly talking about metallogenic epochs. Like for example, the earth was made, the first age of the earth was Archean. It in the geological time scale, it's from 4 gigaeons to 2.5 gigaeons. So around that time, what are the minerals that could be formed? Since at that time oxygen was at its lowest point, so banded iron formations, some of the nickels in komatiites, those are the minerals that has been formed during Archean. Next, we switch to Proterozoic. Proterozoic, the age range is from 2.5 gigayears to 541 million years. Around that, oxygen has already entered the system, but not much free oxygen was there. So in that case, you will be finding the coppers from the Mississippi Valley type setup. Mainly those kind of setups you will find. Next, we are further transiting in the Mesozoics. When the Mesozoics have arrived, next you will find the oxygen levels are increasing. So in that case, you will be finding porphyry coppers, you will finding various hydrothermal systems now entering this sedimentary rocks, metasedimentary rocks, which have been already been deposited in the Proterozoic. Next, when we come towards the end of Mesozoic, when we come to Permo-Carboniferous, that is the peak season of Gondwana. So when Gondwana enters, we all know what Gondwana brings. Gondwana brings a lot of life. Then Gondwana brings a lot of decomposition of these lives, and further you will be able to find coal deposits. And this is how we see the metallogenic epochs. There's a time period corresponding to every mineral that you are finding today. Next, when we talk about a metallogenic province. So when it comes to metallogenic province, we may be saying, for example, for iron ore, when we are considering, we tend to find it around Barbil. We tend to find it in India. We have Shingbhum, this Guru Mohishani Badam Pahar. We have 3 such iron zones in Orissa. Then in the Bastar Cretan, you have Durg. In Orissa, you have Mayurbhanj, you have Sundargarh. These are the iron formations you are having. When we talk about copper, you have Orissa, Surda mines and all. In Orissa, you have this. Then Khetri, there is in Rajasthan for copper. When you talk about lead zinc, there's Zawar, there's Rajpura Dariba. So these are the areas we are targeting. For example, when we are talking about the gold, we mainly go for Karnataka, the Dharwad Creton, for the Hutti gold mines and the Kolar gold fields. So this is how you correlate the time and the space with the mineral deposits you are exploring. Okay. Next, when we are coming to, and another thing that is primarily involved in this is tectonic setting, how they are formed. But for the tectonic setting to be correlated with the metallogenic epoch, with the metallogenic province, and then the minerals, it needs a different class altogether. Of course, the professors of each of the universities have already, maybe when you go to the masters, you will be getting a better insight. But anybody from a primary basic knowledge background wants to know anything, you can definitely text me. I can help you out, since that will take our time, so I'm not going into that. We are mainly focusing to our first part. The first part is when we talk about minerals. In BSc, we have classified minerals into sulfides, sulfates, and oxides, carbonates. But now when you talk about exploration geology, the categories are different. How are the categories working? The categories are working around, are divided into ferrous and non-ferrous, critical, strategic, industrial, and precious. So ferrous and non-ferrous. What is a ferrous mineral? It is highly magnetic mineral. It tends to be more prone to rusting. And the non-ferrous minerals are not that magnetic, and it has a corrosion resistant property. For ferrous minerals, we can talk about iron ore, it's manganese, it's chromite. But when you talk about non-ferrous minerals, it's copper, gold, lead, zinc. These are the non-ferrous minerals. When we talk about the critical mineral, so critical mineral, the basic definition of a critical mineral is it's a ratio between the demand and supply. When the demand of a particular commodity increases the supply, it comes under a critical mineral. And when the demand is less, but there is a supply, or supply is equal to the demand, then also it will be called a non-critical mineral. As you can see, the critical mineral examples are lithium, cobalt, copper, nickel, potash, and rare earth elements. Also today we are going to talk about one of the critical minerals, that is graphite. Now, how do we say critical mineral again? Like, for example, this copper. This copper is a pure base metal. It was initially, for years, it has not been included in critical, but now it is a critical mineral. How? Because of this twin transition phase of green energy and there's green energy and the modern technologies working. Like, we want digitization, we want the modern technologies, we want the this economic development to be at its peak. For that, we need copper. So copper is now included in a critical category. Next comes the strategic. This strategic is a high value. It is a high value raw minerals that are very risky to find out and also to transport. It has a greater import dependency. Like we have to import a lot of these minerals because our country has a limitation up to which it can find out like the mineral in our own country. Graphite is again a strategic mineral. How are graphites helpful? Graphites are helpful in such a way that it has a very cooling property. When the phones we are using, the basic batteries that are formed, it needs a cooling system. The rocket launchers, the reactors that we are forming, it needs a cooler system. Else, when it exits the atmosphere from the Earth, it will melt instantly. So for that temperature balance, we need to put a layer of the graphite around it. So graphite itself has a very strategic. However, copper is not a strategic mineral. Copper in that case are more involved in wind turbines, solar panels, and electric batteries, wiring, basic whatever day-to-day needs are there. That's copper is much in demand. Then comes in the industrial minerals. These are a non-metallic mineral which has different chemical and physical properties. Mostly they are found in chunks. They commonly form generally they form bedded deposits like limestone, potash. There's talc, barite, silica, sand, and gypsum. So these are industrial minerals. Next comes as the precious. That is a rare, high value, naturally occurring inorganic compounds. So these kind of minerals are mainly important because of its rarity, because of its high value, like gold, silver, platinum, palladium, and precious gemstones. Do you know why gold is so precious? Gold has a lot of uses. One of them is it's highly malleable. You cannot make jewelry of copper. It will someday be broken away. It will not be able to hold the bond, but gold has a flow. Gold can be malleably beaten into any shape and it still be occurring years and years after the shape it has been given. So next, when we are done with the categories of minerals and you have already got what are the different minerals. Okay, here let's come. Since I have already worked in Rajasthan only, I am showing you the geological and mineral map of Rajasthan. Let's talk about the geology of Rajasthan. The
Ma'am, your voice is not coming.
Ma'am, you have been muted. Can you please check once?
In the first link, ma'am. Hello, ma'am.
okay, am I audible from the both ends?
Yes, ma'am.
Yes, ma'am.
I do not know how much have you listened. Can anybody please help me catch up?
Ma'am, you were starting about the geological mineral map of Rajasthan.
Okay. So starting again with the geological and mineral map of Rajasthan, let's study this first. Let's describe this map. So we are doing first because we are already done with what is exploration. Then there is describe this map. Okay. So when we talk about the Archeans, the early Archeans, so the first time of 4 gigaeons to 2.5 gigaeons, we are having the Bhilwara supergroup. This is the oldest supergroup, Bhilwara supergroup around. And this Bhilwara supergroup is mainly the banded gneissic complex that you read about in books. This is the oldest of Rajasthan. Next, we come down to Proterozoic. The first rock sequence supergroup you find in this Proterozoic is the Aravalis. These are the Aravalis, as you can see. This is again the Aravalis. The Aravali supergroup is then again overlain by Delhi supergroup. Now, Delhi supergroup has two parts. Delhi supergroup is firstly, it is the North Delhi and then the South Delhi. The North Delhi mainly encompasses till Ajmer. As you come down from Alwar to this, there is a place called Ajmer, south of Rajasthan. Till there, it is North Delhi. After Ajmer, it starts South Delhi. Now, how to distinguish mainly between North Delhi and South Delhi? South Delhi's have a lot of has a few ophiolite suits and a lot of volcanic setup rather than the north. And there are a lot of age gaps also. There are different differences. But once when you travel from Ajmer and southward, you will find a South Delhi setup somehow. Next, when we come up, is as you can see, these greens are the Deccan traps. Okay, these are all the topmost Cenozoic wala parts. These are the recent sediments and the Cenozoic parts. Then here again we have this Erinpura granites. So this is how you study in a brief for Rajasthan's map. If you this is a updated geological and mineral map of Rajasthan. Okay, now why is Rajasthan good for exploration? Rajasthan in itself has a diverse tectonic setting. It has already been formed in proximity to rift basins. It has a very varied setup of a sea to land, and not much further from here the Himalayas have formed. So it has already undergone compressional settings also. So there's compression, there's shearing, there's rifting, there's extension. You have a lot of jumbled up diverse tectonic settings clubbed up in one and only area, Rajasthan. So once you have so much of structures already present in one of the states, you must be forming a lot of traps for the various kinds of oil and minerals together to be beholded in the areas. So Rajasthan is full of mineral deposits. When we talk about the north, there's copper. When we talk about the south, we have copper, lead, zinc. When we talk about the west, we talk about limestones. When we talk about the east, this side, we have copper again. So Rajasthan is diverse. Now in this Ajmer part also, Kishangarh, we have graphite, a long graphite zone ranging around 7 to 8 kilometers. So GSI is already working on it. Talking about GSI, how it is exploring the entire India, particularly Rajasthan, India is already GSI is already done with 1:50,000 of mapping. The 1:50,000 scale mapping is already done. Next comes the STM, specialized thematic mapping of 1:25,000. The particular target of STM is to analyze each of the rocks from a particular area assigned and then find out if there is any particular area rich in mineral deposit. Next comes when 1:25,000 is already done in an area, we tend to go for a G4, that is a reconnaissance survey. The scale for this type of mapping is 1:12,500. So when we go for a G4 stage, suppose for 100 square kilometers assigned to you, or 50 square kilometers assigned to you, you will have to find out a continuity of any mineral you are finding there, any valuable mineral you are finding there. So for finding the continuity, you will have to find it. Suppose you have found a speck somewhere and you tend to find its continuity in 200 meters, 400 meters, further 600. In a double units, you are trying to find the continuity. And then width of the zone that you are trying to find by cutting channels, trenches, etc. So this is how you try to establish a zone, particularly not very much of quantifying, an abrupt so that we can do a detailed mapping there and find out the mineral resource from that area. So once we are done with the this 12,500 reconnaissance survey, next the area is shot into 2 square kilometer or 1 square kilometer, and then we take up drilling. We do the subsurface investigation, and further we take out resources, we correlate the resources, and we tend to give an estimate of the resources that we are having of this particular commodity to the ministry, and further he'll be using that up for the ministry. Hello? Hello?
It's okay, man. Please continue.
Okay. Okay, so we will be further using this data up, and it will be handed over to ministry. So ministry can option this block for further mining. So we are done with the geology and the basic mineral physics, mineral geopolitics and all, how we are doing it here. And next, we are straight away heading over to the case studies we are having. So the case studies that I'm going to discuss today is from the Ajmer district. We are having two case studies, Harmara West Block and Susura Block. So these both the case studies are from critical and strategic minerals. Next comes is from the Udaipur. We are having Udaipur Baswara district. There's a southern district south of Udaipur, that is Gatiana and Gatiana North Block, that has been explored for precious and critical minerals. Next, we have one reconnaissance survey in a Rampura area. It's in Sirohi district for critical and base minerals. So we are starting with Harmara West Block. As you can see, this is one the detailed map that has been prepared at 1:2000 scale. This falls in the topo sheet number 45G/14. The entire yellow part, as I have already zoomed it out, the entire yellow part is a soil covered area. So around 50 to 60% is soil covered, and we have this much of lithologies. This is particularly a quartzite. This pink is a phyllite, ferruginized phyllite. This blue and the gray is an intermediate layer of impure marble or dolomitic marble, as we call it, with interbanding with gray phyllite. And where this quartzite is in contact with the ferruginized phyllite, there appears a lot of hydrothermal activity, which eventually turns this quartzite in contact into a hydrothermally brecciated unit. So it is again a quartzite, but it has been hydrothermally brecciated. We will see how it looks like. And further, we have planned boreholes here to check the continuity of the mineralized zone. The pink is the mineralized zone. You must be thinking, why is the mineralized zone not continuous? Why is the line not continuous if it's a mineralized zone? In nature, we have no guarantee in the subsurface what we are going to see. This is we say it is a pocket deposit. So it appears in pockets. This much mineralized zone is there. Then again, we do not find. We have placed boreholes here, but it did not yield us any positive results. Further, we have planned boreholes here, and we have got results. So like that, you can see these are the boreholes. There's a first level borehole. There's a second level borehole. We will come to know what is the first level borehole, what is the second level borehole, and how are we planning it. But further, if we talk about this, this is a zone that has mineral continuity. This is a graphite targeting project mainly. So as you can see, this black is an outcrop of graphitic phyllite within a ferruginized phyllite. So the phyllite is hosting this graphite. Okay. This is an SP anomaly map. There are a lot of geophysical maps available. There is a lot of geophysical study that we do. As we already know, a scale generally of any geophysical map says that the pink and the red shades are are corresponding to the high values, and the blue and the green tends to say as the low values. So as you can see, the red are the high values and the blue are the low values. So it's a low SP zone, and these are the high SP zone. Graphite is highly conductive. Graphite is less resistant. Graphite has high chargeability because it is conductive again. And then graphite has low SP. Since this is a low SP, so we are targeting these zones for subsurface investigation. We have put boreholes here at 200 meter distance. Particularly this first level to this first level is 200, then this first level to this first level is 200. This is how we plan it. And once the first level is already been proven, we tend to propose a second level, that is further deeper. We propose one borehole to see if the surface, from the surface, we have already found that at this point we are having one mineralization. Now we want to see if this mineralization is further continuing downwards or not. For that, at a second level, we tend to plan one more borehole. If this comes positive, we connect the entire thing till that depth. Okay, so we are corresponding one low SP with this zone, as you can see. Next, we are putting up the high chargeability zones. As I have already told, this pink and the red is high values of millivolts. This is a high chargeability zone. This is a low SP zone. These are very much in synchronization with each other. And with this, you can already see how we are targeting the mineralized zones. We are studying a geophysical map. We are studying the geophysical maps of SP, the IP. There are further magnetic, aeromagnetic, gravity, EM anomaly, and then you have detailed maps. We have to correlate all the maps together to find which are the most probable zones for targeting drilling, so we can find a fruitful result. Okay, whenever we take up exploration projects in any area, we tend to find out the status of the vicinity. Whilst this Harmara West Block was being explored, we had all of this black color G4 has already been done. That means this area has been explored at 1:12,500 ratio scale. Next, when this area was going through already for G3, we had taken up this one block, this other area, block, no? This is another area and this another area. These two areas further were taken up for, again, a reconnaissance survey G4. Okay. This is again a EM over gravity overlay, like SP, like IP chargeability maps. This is also a map we tend to make fall of this EM anomaly maps that we are having. Suppose we have already put up machines in an area, we get lines and lines and various data points. Next, what we do is we tend to join all those data points and find contours. When this contour of EM anomaly is overlain on a contour of a gravity anomaly, we tend to find some common loops. Those common loops are taken up for mineral targeting. See, as you can see, these two blocks are taken up. So these two blocks, there are these loops that are being targeted for mineral finding. So we tend to look for this. Of course, we will be exploring the entire area, but first we are going for this because we have somehow we have a chance that this can be a very positive indication for us. Next, we are coming to how we are planning the boreholes. So for example, I am talking about this borehole. This is a first level borehole, this is a second level borehole, and this is a third level borehole. So when we talk about the first level borehole, we are saying, okay, so this is a first level borehole. As you can see, this is a zone that has been targeted. We have suppose we have a surface indication. In case of soil cover, you will have no surface indications of particularly that outcrop above it. So you will have to study those maps. You'll have to do field study and a lot of walking over your area several times, finding and scratching your heads, and then you will have to plant a borehole first. And then after all the scientific studies done, when you plant a borehole, it tends to come, for example, we are doing graphite. We tend to find it above the water level. So we try to keep its vertical depth lesser. For copper and for other base metals, we're trying to keep the vertical length when we consider the average RL of the area. Suppose the average RL of the area is 445. So we kind of take for any base metal, we are going to go 60 meters down. And for any kind of strategic, critical or graphite type of commodity, we tend to go for 30 to 40 meters down. On a vertical, 30 to 40 meters, suppose we are done with 40 meters vertical depth. So we have come 40 meters vertical depth. This is the point where we want to intersect our mineralization. So we target this point with a borehole, and we have already planned a borehole, for example, 100 meters. So suppose till here we are finding a mineral, and then there is only local lithology and we are not finding any kind of mineral deposit. So we stop the borehole by 10 to 15 meters extra after the mineral commodity ends at some point where we find. This is all done by a visual estimate. That is where your petrography, your all geology knowledge comes into being. You'll have to see the course. You will have to judge yourself if you want to let that borehole go or no, you want to close that borehole again. Kind of that. Once you are done with the first level borehole, we tend to check if this zone body is continuing further deeper. So once we are done with the 60 meters, suppose in here we have done with the 40 meter. So next is multiplied by 2, it's 80 meter. So at 80 meter vertical depth, we are tied to targeting this zone at 80 meter vertical depth. So we tend to imagine this vertical 80 meter, and then we target this point and we do a borehole. For 45 degrees, we are planning for all the boreholes, and then we propose a borehole and it will go further till here. Once we have already find out this mineral body and all, we tend to close the borehole. In that case, you must be thinking, if this borehole has already ended somewhere, why after the mineralization this borehole has been done? Actually, there is a project called RMT. It targets around 9,000 square kilometers and a lot of square kilometers of a huge area of a district it targets. And from there, they tend to find a smaller spin-off projects for reconnaissance survey and G3 surveys and preliminary exploration, general exploration, all kind of explorations they want to do. So they find 2-3 blocks and something. So for them to find out a block themselves, they have to put some scout boreholes to see if there is mineralization or not. So they have actually done the first borehole, this one. Since they have no idea if there is any mineralization or not, they are having a first hand at the for the subsurface investigation. Hence, they plan a longer borehole. So at any point, even if they find more zones they do not know, so they have planned it for 251. And once we have already got, yes, there is a mineralization down there, we have planned its first level to check if there is a continuity on towards the surface 40 meters above or not. And once these two are already been proven, we tend to plan a third level borehole here. Another borehole comes after it later. And once this borehole also, the third level planned borehole also comes positive, we tend to connect all the zones together. Okay. Now in the area, what is the quality of the graphite that we are finding? So this, as you can see, at 72 meters, we are finding this quality of graphite. The more black and soily hands you are finding, the more good quality of graphite you are finding. As you can see, it's not a metal, but it is still giving a very metallic luster, and graphite itself shines like that. At 119.30 meters, the graphite looks like this. The depth at 80 meters, the graphite looks like this. We tend to correlate the geophysical logs around. Since we have already drilled the borehole, we tend to call, once the borehole is done, we tend to call a geophysical party. The geophysical borehole party comes and puts their probe down the borehole up to the, tend to do it till the end, but sometimes due to formation, breakage and everything, there are a lot of situational and aerial problems. Because of that, there may be, they cannot go till further. At least they will try to come closer to the end of the zone, and then they provide us the SPs, the IPs, the resistivity, the magnetic within the borehole, how it is coming, how the formations are behaving. Okay. Next is, how are we going to find in a Harmara West block, how are we going to find the surface indications? Can you see this picture? This is an outcrop of graphite in an area. In an area where you are already having much outcrop, there you can find, as I already said, this is a graphite outcrop. This is a graphite outcrop, as you can see. This is the level of graphite. The hands will be giving a lesser black or lesser grayish streak, because when we talk about the subsurface, it is a very pure form that you are finding from the subsurface. But when it's on the surface, you can see there's oxygen acting on it. There's a lot of factors, erosion and everything. So it will not be giving that good quality of a graphite on the surface. That's why we are doing drilling, for knowing the quality, for knowing the quantity of the resource that we are finding. This is a graphite outcrop again, and these are the graphites that we have broken from the subsurface. There's malachite staining. Malachite is a mineral of copper. This is also a malachite staining. This is mainly carbonate and hydroxide, CuCO3, CuOH whole twice. Total on the surface, we have found a 9-meter thick band of graphitic phyllite was exposed, and it was pinching and swelling. And then sulfides were also found with that. Next, for the this subsurface mineralization from cores, we are doing look at the cores that we have found from all the boreholes. This is RJHM5. As you can see, we have found this is copper, there's graphite, there's ferruginization, there's a lot of copper streaks all over the core. This is again graphite, there's copper, graphite, there's copper, and this is a graphitic phyllite. So these are how the core drilled out cores look like. Next, when we talk about lithologies of Harmara West, how does it look when the quartzite has been extremely hit off by a hydrothermal system, when the hydrothermal fluids have come into their interactions? How have the rocks turned? The plain looking quartzite has now turned into a breccia. Now, many times we kind of confuse it with a fault breccia, but no, this is a hydrothermal breccia. And this is how you find it. You find the box works You find the stock workings. You must have got through Bateman and a lot of books of economic mineral and mineral deposit books, and there you will find a lot of book structures that will be perfect examples of how it should be looking, the stock workings and this ladder veins and all, and this is how they look like in an open field scenario where you go first hand and you'll have to identify a lot of things. Stock works of hydrothermal venation system, hydrothermal brecciated quartzite. This is again a budin of hydrothermally brecciated quartzite in ferruginized phyllite. This, as you can see, these are the foliation planes very finely swerving over each other. These are the ferruginous phyllite, and within that, this is a hydrothermal breccia. So this is a budin. We all know that budin generally forms in a extensional regime. So this is a proof, this is an evidence that extensional regime exists in this block. Next, coming to other structures that we find in the area, there's folding, there's faulting, and then there's again hinge zone of higher order F2 folds, there's shearing. So in a gist, we can say that all the structures that we can read in a book for this faulting, folding, shearing, we are finding everything in this one small area of 2 square kilometers. And 2 square kilometers, I'm telling you, it's more like 60,000 is soil cover. So in a 40% area of this, what to say, in 40% area of outcrops that we are finding all the structures there. See, all these that I'm showing you, this is a phyllite, okay? And these are the quartzites. Generally, phyllite are the best lithologists who can document any kind of deformations they have gone through. But here you can see the shearing can also is very evident in quartzites as well. So quartzites and phyllites both are holding evidences of deformation. Okay, so a few more field photographs I'm showing you. Can you see the hinge? This is a folding in quartzite again. There's a shearing. You tend to find if it's dextral, it's sinistral. You have to go close by. Then I have already showed you the hydrothermally brecciated quartzite budin within a ferruginous phyllite. There's again shearing evidences, tight isoclinal folding with shearing and all on the limbs of the small fold. Now, we tend to find the various kind of structures even in the core itself. So this is highly hydrothermally brecciated. That means the hydrothermal system has entered this particular quartzite and it has intensely fractured and ruptured this whole thing. And since there was iron in the system, it has taken up the veins, the fracture parts, and it's hence named that ferruginization in hydrothermal breccia. We have folding. Of course, this folding is a disharmonic fold since it has lesser continuity along its amplitude. And then there is faulting. We have fewer faults, as you can see. So in core also, you are able to find much good structures. So next, moving over to Sursura block. Previously, we have studied about finding graphite in an area where we have 40% to 30% of outcrops. Now we are talking about an area which has 90 to 94% area is under soil cover. That is no other outcrops you are having. You are simply having a small outcrops in the south. I'll share the map and then you will be knowing. It comes under 45J by 14. The lat long is given. This is the big, if you remember from this area that I have already shown. This was the Harmara West block. And further in that year, when I was exploring this one, the G4 of this block and this block was taken up. Next, we are heading to this G4, which is given again a smaller 1.5 square kilometer block. So we are talking about this G4. Okay, next. So this is that big G4, out of which we have found several other blocks also. But I was assigned this block. This is the Sursura block, which is 90 to 94% soil covered. Okay, and in the topo sheet, it lies somewhere here. So this is the detailed geological map of the Sursura block. As you can see, it is completely soil covered. A few dolomite outcrops are there. When you see such dolomite outcrops, I'm telling you, dolomites do not hold much of the deformation. Even if they have a fewer folds, the folds will be disharmonic. There will be rarely, even the folds when you are talking about, it is not the marble that is holding the fold. The silica veins that encode the dolomitic marbles, they are actually forming the folds, and those are commonly disharmonic. So this marble, these are the carbonates. Generally, carbonates tend to give you an S0. It is a depositional carbonate body, so it may not be deformed. It cannot take up shapes like quartzites and phyllites. So mainly it gives you a S0 bedding plane. Next is this yellow is a quartzite. This is a phyllite. Okay, this much of outcrop in an entire area, and still we are able to find out what mineralization lies ahead. And I'm very happy to tell you all the boreholes here are positive. We have encountered numerously wide mineralized zones in all the boreholes. The width of the zones lay from 2 to 78 meters, and the strike of the zone is 1.43 kilometers. We couldn't place one borehole here because of the local issue. Had it been there, it would have extended to 1.5 to 1.6 kilometer strike. As you can see, there's again a discontinuity here and here. How do we make it? If anybody asks, I'll have to explain. I guess this will take up time. So as of now, I'm not saying anything. If anybody has a question, I can ask how we are drawing these mineralized zones. So as you can see, there's discontinuity and there's discontinuity. This is again considered as a, either it is a very highly folded terrain because it's in subsurface and it's all soil covered. You cannot ascertain it just by one first level borehole and all. So either it is a pocket deposit like Harmara, since Harmara is 4 kilometers south of this block, or this is a highly folded terrain where we are trying to find the continuities within the mineralized zone. For us to find out if this is actually discontinuous or not, we tend to plant boreholes from here. This project has already been seamlessly upgraded to general exploration, that is G2. That means deeper second level, third level boreholes will be done. Infilling boreholes of 100 meter will be done. Since this distance is 200 meter, we'll be planting at 100 meter the new boreholes, and then we'll be exploring how much confidence we have here. The confidence, if the zones come here, we'll have a greater confidence level that these zones are connected and all. For that, we do deeper drilling and infilling boreholes. Next, again, I am sinking all the SP and IPs. As you can see, this zone, can you see this zone? The mineralized zone that we are finding from the subsurface data from the drilling by core logging and everything and chemical analysis, that exactly lies on the low SP zone. And again, if I talk to you about the high chargeability zone, I told you pink and red corresponds to the higher values, blue corresponds to the lower values. So this is a high chargeability zone, this is a low SP zone, and the zones are very well lying on the high chargeability and low SP zone. This is how you correlate your maps. Next, we are coming to the detailed map again. So for example, this is our borehole. This was our first borehole, after which after it has turned positive, we have drilled 2 more boreholes, north and south. Then the north borehole has yielded a zone like this. See, the first zone is 54 meters wide, the next zone is 3 meter, then 2 meter, 5 meter. These are the numerous zones that we have found. The core of graphite looks like this. And when you tend to find what is the good quality of graphite, you tend to soil your hands and see how much darker it is showing. Graphite is not alone in the system. Also, there is another critical mineral called vanadium. Vanadium is also present. So vanadium zones are this much. Now, how is this vanadium present? Vanadium has no mineral phase here. Graphite has a mineral phase here. Since graphite is totally lithologically controlled here. This graphite is held in the phyllite that is present in the area. The carbonaceous phyllite that we are having in the area, it is totally lithologically controlled and not structurally controlled. So graphitic phyllite is the main host rock we are having here. And in that graphitic phyllite host rock, there is clay present in the system. So the clay has a lot of empty lattice spaces. This vanadium has entered the entire system of Proterozoic metasediments during the Proterozoic itself. The vanadium has come at that time, the carbon has come at that time. The carbon has been further metamorphosed and enriched and upgraded to graphite, and the vanadium has taken up the lattice and the void spaces as ionic form within the clay that's present in the in the graphitic phyllite. So graphite has a mineral phase, graphitic phyllite, but vanadium has no mineral phase. It is present in an ionic phase. So further, when we talk about the second borehole, once this borehole, I have told you already that this borehole was drilled, this was positive, so we have drilled this borehole. Once this borehole is also positive, we have further planned around 200, going 200 meters north, and we have further planned on one more borehole that has also come positive. As you can see, the sections of the boreholes. You may not find this line very straight. You may be finding this line has a curve or something. This is because of the deviation of the borehole. The deviation of the borehole is again determined by the HF test, which again, if somebody wants to know, we can discuss. This is the quality of graphite, and this is the geophysical log that I've already shared, how it is being prepared. This is the second level borehole that we are having in this area. This is the first level borehole that is positive, so we wanted to check in a deeper continuity if this mineralized zone further continues deeper or not. So here we have already found this much of zones in the first level. So we have again targeted this zone at a much deeper level. Suppose this is the zone continuing. We have targeted it here. But however, nature no strict rules that I'll have to come here and there. No. Since there is subsurface folding, so maybe this zone has folded till here. So when we join it, it will be something like this. That is, it is a folded body. Okay. So we have drilled this borehole again come positive. In maybe general exploration, we'll be drilling one more borehole behind it to see if it is continued further down, if this borehole is coming completely straight down, if the mineralized zone has a continuity in deeper areas or not, like that.
Ma'am, screen sharing got stopped.
Screen sharing got stopped? Okay. Now is it visible? Is it visible?
Yes, ma'am.
Yes.
Now when we talk about how it looks, how the graphite looks in thin sections. This is how the graphitic phyllite looks in a thin section. These are the chalcopyrite with the graphite. There's again graphite with the quartz, with the biotite. This is how this is a lensoidal form. That means the graphite is actually a phylitic body. Okay, so it swerves around the larger quartz fragments. It cannot change its path. It cannot make the quartz fracture and make its path. It is a lighter body than the quartz, so it will be swerving around the quartz. Okay, talking about the structures that are found in Sorcerer block, even when we have 5 to 7% of the outcrops in the area, in the entire soil covered area, you are still bound to find some good structures. And here I'm sharing some. We are having 2 generations of quartzite in one. As you can see, this is one quartzite and this is the second quartzite. How are these quartzites formed? It says this is a relic compositional banding we are finding. It's a relic bedding. The first generation of quartzites, for example, if we talk about the sedimentation history, quartzite has a protolith of its prototype is sandstone. First, the sandstone was deposited in a basin, and then the sandstone was later subjected to metamorphism and all, and it has formed the quartzite. Later on, the quartzite has been deformed. It has a lot of fracture channels formed, and a lot of several hydrothermal fluids have entered the system through those fractures. Next, if these fluids were rich in silica, they would deposit the quartz vein within the layers, within the fractures and all. And over years and years of metamorphism, for example, I've already discussed about the metallogenic epochs. In Proterozoic, we are having this deposition of sandstones, metamorphism, etc., sedimentary things and fracturing and all. And in the Mesozoics, we are having a hydrothermal system being active, and all the hydrothermal deposits, the epithermal, telethermal, hypothermal, mesothermal deposits coming into play. So around at that time, maybe those hydrothermal fluids, silica rich, have entered this system, and later on they have been metamorphosed and crystallized, and the older quartzite would have been remained as a relict, and the newer quartz vein that were laterly deposited have formed the total unit of the quartzite, holding the older quartzite. Next, we can see the shearing evidences. We can see the widely spaced cleavages with the microlithons. We have this negative flower structure, as you can see. Maybe you have read about forming hosts, grabens, in smaller scale. These are in core. There's two generations of veins, as you can see. This is an earlier generation of veins, later intruded again by a next generation of vein. This is hydrothermal brachia, with the brachia fragments having sharp angular edges trapped within a hydrothermally activated quartz vein. Next, as you can see, this may be looking like a fault, but this is not a fault. At times, the folds tend to rotate and tend to be sheared so much that one of the limbs tend to give away. And there is actually one more limb here. You may see this white line. If you have a very clear vision through a heart sample, you would be getting to know that this is a highly sheared fold rather than a fault. And then I have shown you this is how the graphite looks in a core box. We have already cut 50% of the core for sampling, and so the remaining 50% is here. The graphites are here. This is like an epidotized and chloritized phyllite being trapped within a quartz mica schist. This is a quartz mica schist rock. Later on, it has started transforming and engulfing the rock from all sides, and this much relict is remained. This is again this hydrothermally highly fractured system. As you can see, there is no particular direction, no particular any kind of synchronization in the veins, in the fractures. The veins have intruded and they are forming an anastomosing network of veins. And this is again epidotized and chloritized veins. Now, chlorite are primarily of two types when we talk about its composition. There is one magnesium aluminum rich, there is one iron rich. Now, when we talk about an iron rich chlorite, we tend to talk about this chlorite will appear a little brownish and reddish. When it is magnesium rich chlorite, it will tend to appear a little bit of kind of khaki green color. We say khaki green color will come around in the chlorides of magnesium aluminum rich chlorides. This is a longitudinal vertical sections. That means all the boreholes that I've already shown you here. All the boreholes, as you can see. Okay. From this also you can of course discuss what was the primary setup of the sedimentation when it happened. How has this rock formed from? What is this basin? Is it a basin? Is it a hill? What was it in the primitive times? That also you can around discuss from the protoliths of the now formed rocks that you are seeing. And of all the boreholes we are seeing, we are drawing one longitudinal vertical section. Here, as you can see, these are the zones that we have encountered in all the boreholes. I've already said all the boreholes are positive. So we have found all these boreholes and we are seeing like that. What is an LV section? What is a cross section? What is a map view and everything? How to correlate them? That also I can explain, of course, if anybody is not getting bored and anybody is unable to understand. So I'm done with the critical and strategic part. If anybody has any questions, they can definitely ask.
Ma'am, with your permission, we would now like to move on to the question answer part. Hello?
Okay. Yes.
Okay, ma'am. First of all, Kaushik Dev Sharma asks, there have been cases where locals ask geological survey teams to leave, fearing the loss of their land. How do exploration teams handle such situations?
You are asking, actually the voice is echoing, so I am just repeating a question. You are asking that there is a loss of land, maybe because of there are private lands their own, and we are drilling and we are exploring in their areas. So how are we dealing with that? Are you asking that? Just a second. Okay. So, see, when we tend to plant a borehole in their areas, we tend to give them a compensation. For example, the much area that is going to be used, we will see the whether it is grains or whether it is a vegetable they are growing, or whether if there is a house settlement, we are not going to do anything for that. We will shift ourselves till it is coming in an empty space rather than on the head of anyone's house. Okay. So we will shift our boreholes. We have the full liberty of doing that based on the circumstances. When we talk about exploration, there are three axes: E, F, and G. E is economy, F is feasibility, G is geology. We are only dealing with the geology. Economy is not our part because we are not commercializing our things. Our work is to survey, to find out, and to hand over to ministry. There is another aspect called feasibility, that whether the ground is okay for drilling or not. This is when this comes into play, that we tend to suppose it is someone's farmland. In Rajasthan, there are many farmlands, and this is a very common issue. I have faced, there are a lot of issues when it comes that they do not want us to do work there and everything. But then again, you'll have to, we tend to keep our laborers there. The local ones only will make them understand in their own language. We offer them some money for the area being destroyed for some time. We tend to dig up a total area, make it plain, and then we have to put the drilling machine there and everything. For the primary time being, we do it and then we compensate by giving them some money. And next comes is, since the machine already being standing there cannot be removed in one day, it will take suppose a month or two for the drilling to be completed. We tend to keep the land's owner as the watchman. So for labor here in labor rules, they already have a certain amount from the Ministry of Employment and all. They have a particular set rule of this much payment will be them for per day. And since there are 30 days, suppose a borehole has run for 30 days, for 30 days into X amount will be given to them. If we tell them, you be the watchman here, you take care of the machine also, don't let anything be stolen away, and we will give. So they're getting a crop money already, and they're getting a watchman money. And further, if they think they want to do some work in the drilling, has a lot of work. You have to lift up heavy pipes, you have to do a lot of transiting things and all. They can also help there also they can earn money. Okay. So we tend to give them some payment, we tend to give them some work, some labor, and this is kind of a mutual understanding you'll have to do. There's no hard and fast rule that you will be able to remove them and all, because it's their own land. We cannot just go and stand there and say no, you will have to leave. So it's totally because it's a public dealing thing again. So depends upon a lot about your own behavior. For example, they have kacha houses, they do not have not a very good house. When you go there, it will be very much broken and shabby and all. But you have to be very much grounded. When you work in a field as a field geologist, you cannot be a high society, high class person. You have to be very basic as you know. No matter what life you live outside, there you have to sit in their angan, you'll have to sip a tea from them, you'll have to consume water from them, and you'll have to bow down to them. Only then they will bow down to you. It's a mutual respect thing, and we have to do it like that. For us, we are only doing survey. So this is the maximum we have to deal with. When the mining comes, that is totally up to them how they are dealing and all.
While mining is necessary, it also causes environmental damage. So, how can we balance development and sustainability?
See, when they are mining, again, I'm telling you, I'm from a survey team. I'm not a mining team. But when we talk about mining, government has, when you open a mine, you have a lot of investment to be doing. You have to propose a complete plan of what all setup you are going to do, how much money you are going to invest, how much money you are going to return to government as a performer, in what form, in what EMIs or installments you are going to give the money to government, what are the developments you are going to do in a area. Suppose I have gone to a remote area, I am there very much responsible to generate employment. I am there very much responsible to open hospitals, schools, and everything. All the mines, like suppose Rajpura Dariba mines, they have hospitals themselves, they have medical care, they have schools, small schools. They are very much responsible for taking care of the entire area. They have to make an entire township there. They also have to give a plan and a budget for the environmental sustainability again. Whatever waste they are producing, they have to dispose it of themselves, and that is included in the plans they're giving to government. In that case, you may be seeing a lot of reels and all are viral that Yamuna Nadi and a lot of nadis from the Jharkhand and Odisha are getting polluted because of it. It is totally illegal. That is why people are sharing the reels. They are coming forward with the thing. Previously, we had less access to internet. Post COVID, these things have come up more into eyes because now digital India is so much active. So people get to know this. But I'm telling you, all the waste management is already included in their pro forma when they submit it for mining mines they are going to open. They do not do it. That is completely their problem. That's completely their. Yeah, you can definitely call out. You can take legal action for them, against them, of course, because when you start a business, you of course have to give a total what losses you are going to deal with. So how you are going to deal with the losses? What are the profits? How are you going to share the profits? What waste management you are doing? They will have to be very actively doing it. Now there are a lot of companies they do not do it. That is of course a good bad problem. Yamuna Nadi is getting polluted, and there's a lot. But then again, if you one day think that, ma'am, this is a very wrong thing they are doing, you can definitely call out, because in their performa they submit to the government. It is already included waste management now. I hope I'm able to answer the two questions that you have asked. Anybody having doubt in the two answers I have given already?
Ma'am,
Anybody?
may I move to the next question?
Yes.
This one's from Snigdha Suchishmita Khatua. She is asking that what are the digital mapping tools that were used in this activity and what their purpose was.
Okay. Digital mapping tools, you will have to know ArcGIS. This is basically a very basic tool for mapping. In college levels, we tend to come to this QGIS and all. When you enter GSI or any survey team, you have to know for the map portion, you will have to know ArcGIS. The training has been provided by the institute itself. Second comes is the AutoCAD. That is not provided by the institute. In some places it's provided, in some places this is not provided. But then again, you get to learn it from the people around and all, and by your own enthu, you can learn it. The vertical planning of boreholes are done in the AutoCAD, and once all the boreholes has given us zone and all, we tend to form a 3D modeling, that is through SARPAC or Datamine. So these are the softwares that come into play.
Thank you, ma'am. Next one is from Krishanu Mitra. He is asking, what are the most overlooked unconventional geological settings that could potentially host significant concentration of REEs and lithium?
For now, as of now, the REs are mainly looked on for the granites and the cyanides and all the alkaline rocks and the silica-rich rocks. Those are the main targeted lithologies for RE. As of now, this is the current approach in India. We are yet to find a lot more of scopes in it, since we have already declared REs as critical. It is highly hunted down in GSI. This year we have taken a lot of projects in granites and all the Sivana and the western Rajasthan has and the southern Rajasthan has a lot of granites and all, and we tend to target those lithologies for the REs. And other lithologies for targeting RE and all, Previously, maybe REs were present in the iron formations, but India has lesser technologies and was not developed at that time, was not ready for extracting REs and other critical minerals from there. But now that jab jago tabhi savera, so now they already know that this is going to happen. We have to keep our eyes and ears open. So the different geological settings that you are asking, it's totally we do not know what setting we are going to find out. Maybe the see, any kind of granite intrusion is the last phase of deposition that will be occurring in any area. The intrusives come on the top of any stratigraphic sequence you are studying. So the tectonic setting, whatever lies down there, you have to study the entire area first, and then you come for the granites. So they are targeting the mineral particularly, but then again we have to read the entire area and then the last part of the intrusives.
Thank you, ma'am. Ritvik Bishwas asks, how do you determine the flower structure from the core?
Okay, so have you read Earth Structure by Plume and Marshall? It's a very good book. I would recommend everyone to read from it. There's this negative flower structure. The positive flower structure is when there is transpression or transtension. That is, there is a shearing movement and then there is a compression or extensional movement. When we talk about negative flower structure, it involves a shearing movement with a extensional regime. So when an extensional regime happens, we all know there is a normal faulting that happens. But again, then there is a shift of planes and all. Not only from that one photo we can differ it. There are refer to it. We have a lot of evidences from the course which shows shearing as well. There's extension as well. There's faulting and all. So from that only, when we could see the host and gribbons and somehow the lithologists have slipped past each other and gone down, we can see fewer host and gribbons, and it kinds of shows as multiple planes and multiple splays of one single fault coming up. We are referring to it as a negative flower structure. Had it been that one of the center part would have gone up and then a little bit of like the faulting will displace the beds as this, then we have called it a positive flower structure. Since it is like this, that's why we are calling it as a negative flower structure. The center part has sunken down and forming hostel ribbons with evidences of shearing. Okay. I hope it is
Thank you,
answered.
ma'am.
Yes.
One last question which we can take up now. It's from Deeprapal. When someone joins GSI as a geologist, do they receive formal training from GSI in exploration techniques and field methods, or are we expected to learn most of these skills during our studies and internships?
No. When you come to GSI, they spend a lot of money training in. You are their asset now. GSI takes you in as their own. So they will tend to make you understand from the ground zero. You will come here and you will learn how to take a data from Brunton compass. From there you start. From locating yourself to a Brunton compass to taking data, you'll be starting from there to the advanced level of geology in different diverse terrains. You'll be studying. You are taken to different places. For example, Himalayas, they have a module. The northeastern part, they have a module. They have a module in Rajasthan, and then Hyderabad, there's software, and then there's Dharwad and southern regions, which have a different tectonic setup of older regimes like Archeans and Proterozoics. So in different tectonic setups, in different geologies, in different areas, you are given training from the very ground zero, and whatever silly questions you may think that I am so old, I have completed masters and still I do not think if you will be employed in a batch of 50 or hundreds or maybe more. You'll be standing there, you'll be asking silly questions, and then you will be thinking, no, I shouldn't ask because people will laugh at me. Please do not think like that. GSI is already investing money for you to learn. So someday you are going to do magnificent work. So GSI takes you on as a student. You do not come as a professional. Now you will be shaped up into a professional geologist, but post training. So there is an extensive level of training you will be doing from ground zero. So no need to think that there you have to learn and come with a preconceived notion and prejudices that I'll have to know everything. No. As much bookish language as you can collect from the books and you appear for an exam, and a few field experiences that the colleges provide. You'll come here, you will learn as a professional geologist now.
Thank you so much, ma'am, for such an insightful and inspiring session. It was truly enlightening, and we appreciate the valuable knowledge you shared with us. We also thank all of you for your enthusiastic participation and thoughtful questions, which made the session truly engaging and interactive. Lastly, I would like to ask ma'am to share her feedback and views for our Geoscience Society. Ma'am, please.
Hello. Yes, I'm. This Geoscience Society is really. It's very nice and very highly of you to have considered me to show you a few basics of exploration geology. Yesterday, I was talking to one of the students from your group, and I was asking him how you all have like put together and come together as a team to work like this, and he explained me a few points which were very interesting. In our times, if I tell you truly, it was not that convenient for all of us to join up on platforms. There was Facebook and all. There were a few geo clubs they have made, but there was very less interactions. There very less of digital India into being. But now the younger generations, you are the future geologists. You are going to be the best and the best creamy layer of the society who will be coming and joining few in GSI and few in other children organizations as well. GSI being the most oldest organizations, take all the there is no gender bias, takes all of the employees as their own, and they'll teach you from ground zero to an advanced level, and you will be learning a lot, you will be working a lot, and someday you'll be feeling proud of yourself that I'm here. And so, with this Geoscience Society, you have already taken up such a good initiative for your bright future that I would like to congratulate all of you. You guys are doing so well. You guys are already so enthusiastic. You guys are so learned that I wish you all the best. You guys are doing superb. And thank you, Geoscience Society, for all the respect.
Thank you so much, ma'am, for your kind words. Now over to you, Aritru.
Thank you, Koyana. Hello everyone, I am Aritru Mukherjee, currently serving as President of Research Wing. On behalf of the Geoscience Society, I would like to express our heartfelt gratitude to everyone who made today's International Women's Day special talk a great success. First and foremost, I would like to extend our sincere thanks to our esteemed speaker today, Ms. Saha. I hope Ms. Saha's words and experience have helped our young geoscientists building a sustainable future. Also, we are truly grateful for your presence and motivating the young minds here today. And a special thanks to all the members of the organizing teams and the wings. Lastly, I have an announcement to make, actually two. As today is Women's Day, we have a special quiz which will be posted on our Instagram page. And after very much waiting, we are finally organizing an online symposium on 14th of April. The details will be posted on our social media pages. So stay tuned. Thank you.
Ma'am, I think we can now end the session.
Okay, okay.
Thank you so much, ma'am, for your time.
Thank you, ma'am.
Thank you.